Hey, Danielle.
Hey,
We got a few minutes, but you're welcome to ask me questions as always. You can also go ahead and type in your first and last name so you don't forget to do that.
sounds good. Thank you.
No problem. You're welcome.
I do have a question about the homework due date
Okay.
for I think it's chapter 22. Will it still be due on Monday, even though our test is due Monday?
No, I went ahead and just like 2 minutes ago, I just changed it to the 23rd, which I think is Wednesday night.
Oh, okay, sounds good. Thank you so much.
No problem. So yeah, that's chapter 22, and then chapter 23 is due the following Sunday. So hopefully that helps. Keep the hat. Keep the hat. Have you scheduled a time for you to take the test? Or are you taking it at home or what you got planned?
Yeah, I scheduled it for Monday, I think at 10 a.m., 9 a.m.,
That's
something
cool.
like that. Yeah,
Good deal. Well, good luck on that.
thank you. I'm
We
gonna try
have
to study all weekend.
we have had some good grades, but we had some low grades too. So hopefully it'll pan out.
Yeah, hopefully.
I'm sure you'll do better than you know. I see you chatted your name, Gabriel, or is it Gabrielle? Sorry. Uh,
It's
feel free-
Gabrielle, but no worries.
I thought it was. I have Danielle and I have Gabrielle, and both of those, if it's not for the ELLE, I wouldn't know what to do. So,
Yeah, sure.
well, feel free to ask questions if you have any. Heck, we only got like 4 minutes left anyways.
So just to confirm, we have until Monday night to complete the test in person.
Yeah, I gotta send something to the testing center, let them know that because I've found some students are wanting to take me up on it. So yeah, you can do it Monday night, no problem, or up to 11:59 Monday. Of course, whatever the testing center's doing, that's you got to figure out the schedule with them and what they need. Or like I said, some people are actually doing it with the Respondus lockdown browser and Respondus monitor. I've got to make a separate test for that one.
And then are we supposed to get permission or notify you if we're trying to do it with the lockdown? And
Yeah,
I mean, okay,
you just let me know what day you want to do it and when you're doing it. Basically I have the ability to come in and watch you at any time as well, so that helps me a little bit. So just let me know when you're planning on doing it and what day, what time of night, and all that sort of stuff, and I'll take it from there.
okay, thank you.
You're welcome. Hey, Carter.
Hey, how are you?
All right. I went to the dentist today and I looked back and like I was just sitting there and all of a sudden I see somebody, it actually looked just like you. And I'm like, is that one of my students? And, I'm so old now that like my students are like old enough to go to med school and already be finished and be career, dental or dentists or career physicians or whatever. That's where I thought it was you. And they said, oh, I'm such and such. I was like, oh, okay. That like they walked in like with no fanfare, and I thought it was like just someone recognized me and came in to say hi, and I looked, it looked like you. And then she took her mask off and didn't look like you.
Oh, I mean, I probably would do that, but probably be a little bit silly. They'd be like, "Why is this random patient walking back to another random patient?"
Yeah, that's pretty much the way I behave. I just walk into random places like that. I mean, it's okay at a
Yeah,
dentist. I wouldn't do it at a doctor's office or something.
right.
I got another people coming. Another people. That's weird. I feel like I know that name, but I'm not going to answer it. That'll teach him. I should probably mute my phone. All right, got about a minute left, folks, and then we're going to get cracking on some more Gauss's law stuff. Of course, you do have a chance to ask me questions about anything. I hope I'll get some time to make some stuff up this weekend regarding some videos and stuff. I probably won't be able to post them till Monday night or whatever, but anyways, I hope to have some more videos posted over the weekend, even if I don't get them done till or don't get them posted till Monday. My reading glasses are perfect for reading, but they make it essentially impossible for me to do anything but reading a book close up to me. So like I'm looking at my screen, I can't see anything. Almost time. It appears everybody has already chatted your first and last name, so I need not say that again, I guess. Yep, every one of you have. All right. Well, I guess I'm going to go ahead and get started, and I'll ask again. Does anybody have any specific questions on anything? Maybe perhaps, practice test questions you've had going, preparing for the test, or any other kind of questions? I did just answer one question regarding chapter 22 just before I came in. I took both chapter 22 homework and conceptual and set them due to October 23rd, which is Wednesday night, 11:59 p.m. So they were originally due at like Monday night at 11:59 p.m., but now I moved them back to Wednesday. So you just have to have them done before class on Thursday. So we do have that set, and the following chapter 23 is supposed to be due a week from this Sunday. So you technically don't have anything that you have to get done by this Sunday, but you do have something by Wednesday. And I would actually recommend you do it anyways, but at least you have another couple of days if you don't. So no questions? All right, well, let's get started with Gauss's law. So last time I did give you a little bit of introduction, if you will, to some of the coordinate systems. Specifically, I talked about spherical coordinates, and I showed you a little bit about how cylindrical coordinates were this sort of the two-dimensional or the three-dimensional analog to polar coordinates. So the main reason we need to, I say we need, the main reason I use that at all is just so we can use those particular vectors, because if you actually understand those particular vectors, the vector r hat, theta hat, phi hat, k hat, if you actually know what those vectors are and the direction they push, you can more easily describe exactly what direction the electric field acts in. And more importantly, when we get to the magnetism, you'll have even that'll become even more apparent. So anyways, that's the reason, and the only reason really why we're doing that is for clarity. But again, you're not necessarily required to know spherical coordinates or cylindrical coordinates, but I'll certainly give you a help on them if you want. You can actually do a Google search for that on my YouTube channel. I actually did I think a 3-part series of coordinate systems, so you can look at those as well. I did just see another person logged in. I just want to remind everybody, make sure actually, it looks like both of you already did, but make sure you chat me your first and last name. We're going to start off on Gauss's law now. We did a Gauss's law application, and we did a pseudo derivation of Gauss's law. Mainly, we did a derivation of a specific case of what the electric flux around either a point charge or a spherically distributed charge that was at the center of a Gaussian surface. We were able to figure out what the net electric flux flowing out of that spherical Gaussian surface was, and we were able to determine that the net flux flowing out of that that Gaussian surface was Q enclosed over epsilon naught, and that is the actual Gauss's law. So now I'm going to go ahead and share my screen, and we're going to do a couple more applications of Gauss's law so you can see how they're done. Again, what you want to think about is listen to my words and Notice how the left-hand side is supposed to be really, really easy, how it's always supposed to reduce to electric field magnitude times an area, period. It's always, the left-hand side is going to become that, or it could, in certain cases, you could literally just get zero when you're trying to compute the electric field. But generally speaking, it'll be electric field times area, maybe another term with electric field times area, and then maybe another term that's zero, or sometimes it'll just be one term that's electric field times area, and the other terms will be zero, or sometimes all the terms will be zero. Okay. So you're looking at this right now. I want to reiterate exactly what Gauss's law is in the form that we're using it. And in the form that we're using it, it's the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And I want to remind you that Q in general, not just for enclosed, but in general, can be equal to the integral of lambda dL, or the integral of sigma dA, or the integral of rho dV. So just for the record, the units of lambda would have to be coulombs per meter, whereas the units of sigma would be coulombs per square meter, and the units of rho would be coulombs per cubic meter. And hopefully that tells you or reminds you that dl is literally like a dx, dy, dz, or dr. A dA is, like 2 pi rdr or something like that. It's literally a differential area element, and dV is a differential volume element. So now that we have that, I'm going to set up a problem to solve in a coordinate system so that we'll already have the coordinate system. And I'm going to use Gauss's law to solve this. And this is actually happens to be a problem we've already solved, but we solved it in the more difficult way of using Coulomb's law in integral form. Okay. So what we're going to have here is an x-axis pointing this way and a y-axis pointing this way. And we really don't need a three-dimensional axis or coordinate system here. I'm just going to stick with it this way. And what I have is a wire that's infinitely long and aligned such that the y-axis is along the symmetry axis of the wire. So when I look at this, top and bottom, they look like that, but they go on for infinity. Now, again, that's just a construct. We know that physically we can't have anything that is infinitely long, but the main point is in the physics world, most of the time you can call something infinite when the distance away is at least a factor of 10 larger than the distance that you're dealing with regularly. So for instance, if I'm talking about trying to find the electric field some distance away from this wire, if I wanted that distance away from this wire to be 3 centimeters, then bare minimum, I would want the ends to be 30 centimeters away from that spot. Really, I'd prefer 100 or even 1,000, but a factor of 10 is usually enough. So what this is a uniformly distributed charge lambda. So I'm going to draw a line like this. Say a uniformly charged infinitely long charged wire with a linear charge density, willy-nilly. of lambda. Exists and we want to find E a distance R from the wire. Okay, so that's our problem. We want there exists a uniformly charged infinitely long charged wire with a linear charge density lambda exists, and we want to find E, a distance R from the wire. So what I'm going to do is I'm going to imagine that the distance R is about about 3 blocks basically. So this is our distance R right here. And I want to know what the electric field is at that particular point. Okay. So E equals question mark. Remember, the process with Gauss's law is we have to understand Coulomb's law to some extent. Like we need to know the Coulomb's law for the electric field or for the force, so we can get a sense of what the shape of the electric field is, because we're going to make a hypothesis about the shape. And then we're going to plug that into the left-hand side of Gauss's law and compute the left-hand side. And then we're going to plug that, use the right-hand side of Gauss's law and work out that. Then we're going to take the result of the left-hand side and the result of the right-hand side, set them equal to each other. And that's going to allow us to solve for the magnitude of the electric field. Because we are going to make a hypothesis about the electric field, but it's a hypothesis about the magnitude, the direction, and what variables it depends on. Okay. Now, the secret of this is, one, you want to make sure your Gaussian surface actually intersects or goes right through a point at which you wish to know the electric field. So, like, for instance, here, I know for a fact that I got to go through that point where I drew the arrow and wrote E equals. I've got to go through that with my Gaussian surface. Another part of the trick is the Gaussian surface. In order for the left-hand side to avoid actually having to do calculus integration as opposed to just symbolically do it, you actually need the electric field to, one, be a constant on some part or all parts of the Gaussian surface. So the electric field needs to be a constant on it. And by doing that, there's actually a second result that happens. That means that the actual surface would be an equal potential surface, but also the surface would be perpendicular to the electric field. So choosing a Gaussian surface or a part of a Gaussian surface on which the electric field will be a constant is equivalent to finding a surface that is an equal potential, and it's also equivalent to finding a surface that would be perpendicular to the electric field. Then all the, well, I say perpendicular, reminding you that the electric field would be perpendicular to the surface, which makes it parallel to the area vector that represents at least a small part of that Gaussian surface. If you have multiple parts of the Gaussian surface, then hopefully at least one of those will be able to be done that way. If you can't get any of those surfaces made that way, then that's going to be a result where you couldn't actually solve Gauss's law for the electric field. So it's not that Gauss's law doesn't work. Remember, I told you it's Gauss's law, not Gauss's helpful hint that sometimes works. It's more a matter of specifically doing this weird thing of solving Gauss's law for the integrand is a really hard thing to do, and you can only do it under very specific symmetries. Those three symmetries are infinitely large plane, a infinitely large cylinder, or even an infinitely large, infinitesimally thin wire. That's sort of what I'm doing in this case, is an infinitely thin one, but later on you'll see that we'll do it for a finite thickness wire and also for a sphere. So you have to have infinite plane, infinite cylinder, or a sphere. If it's not one of those three symmetries, you can't use Gauss's law to compute the integrand. Okay. So that's what we're trying to do here. I'm going to go ahead and write down that the solution is, so I'll say solution. And when the solution's written, of course, what I mean by that is that's where we put like some of the things we're going to be using. I'm going to use, for instance, Gauss's law, which says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm going to use the idea that Q is equal to the integral of lambda dl, stuff like that. And that's pretty much it. Okay. Now, I do have to draw a Gaussian surface that is going to be, for instance, right through the point where I wish to know the electric field. So what I'm going to do is I'm going to imagine a line going right through here, because what I know is when we did a problem like this using Coulomb's law, we found that the electric field of an infinitely long wire was inversely proportional to the radius, and it was proportional to lambda. But that's pretty much all we know, and I'm not going to go on that assumption. I'm just going to make the argument from a symmetry standpoint that clearly only the electric field should only depend on the perpendicular distance from the wire. In other words, if you took and measured a distance that was perpendicular to the wire and you measured it out a distance r, then the magnitude of that r should only depend on that value, or excuse me, the magnitude of that electric field should only depend on that value r, which you can tell if we put it in a different type coordinate system, that r might be the r that we know of from polar coordinates, because it'd just like be in the XY plane, and then the wire would have been parallel to the Y-axis in that case, or excuse me, to the Z-axis in that case, and we would be looking at it like that with the little R's pointing out. I don't expect it to depend on, for instance, the variable Z, which in this case, the Z-axis would go into the board. I do not expect it to depend on Z. I do not expect it to depend on Y, and that's because the symmetry of it. For instance, if we thought that maybe a little bit of, let's say, imagine a little individual charge right here is going to cause an electric field at this point, and that little charge would cause an electric field at that point to point like this. So there you'd have a particular value of Y, and here you'd have a different value of Y, which would give you a different E field. But what you'll notice is that particular electric field like this and that particular electric field like this both have Y components as well as X components. And from symmetry, you know that there would be an equivalent Y component for this one that has the opposite sign, and again for this one as well that has the opposite sign. So any of those Y components would have canceled each other out just by symmetry. So that just leaves us with a component that's parallel to the x-axis, and it would be very unlikely for that to depend on x. So what I'm going to do is I am going to say that my hypothesis is the following. So here's the hypothesis I make regarding the electric field. I think the electric field E is going to be some function of r, which really is a distance away. That if I had chosen to put the x-axis, or let's say I chose to put the y-axis to the right where the x-axis is now, and the x-axis coming out of the page, then the z-axis would be in the page and be straight up. In that case, the r would depend on x and y in some sense because it's going to be in the xy plane, but really r gets it because you don't really care about whether x is 0 and y is r, or y is 0 and x is r. So I'm going to say it's E of r, and then I'm also going to say it's going to point in the r hat direction, which is the r hat from cylindrical coordinates. So I'm going to say r hat and put a sub c on it. And that just means, remember, the r hat from spherical coordinates had a I hat component, a j hat component, and a k hat component. Whereas if you were in 2 dimensions, the r would only have x and y's, and therefore would only have I hats and J hats. That's the way this one is. This R hat only has I hats and J hats. It's never going to have a K component. Okay. Because of that, we realize that if we had a constant R, then the magnitude of the electric field, based on my hypothesis, should be a constant as well. So that means this green line should actually be the right-hand side of something that has a radius of R. So the left-hand side should also, of course, have a radius of R. And I'm trying to do 1, 2, 3. So in this case, the Gaussian surface is going to be a cylinder again, but the cylinder is going to look like this. And this, like that. And additionally, it's going to have a length L, and obviously I think you can tell it has a radius R. So that's our Gaussian surface. I'll label it as such. So that's our Gaussian surface. And now I'm just going to start with the left-hand side. So left-hand side of Gauss's law. So make a note of this. This is the way that I found most efficient to apply Gauss's law, because it's this weird equation where you're not working one side to get an answer. You actually have to work both sides. And then you have to set both sides equal to each other, and then you have to solve for the answer. So the most efficient way I've found is to work out the left-hand side, calling it LHS, work out the right-hand side, calling it RHS, and then set LHS equal to RHS and solve for E. So the left-hand side of Gauss's law is just going to be the closed integral of E dot dA. In case you didn't hear it yesterday, that circle on the integral is sort of a mathematical reminder that Gauss's law does not apply unless you're doing an analysis of a closed Gaussian surface. In other words, the Gaussian surface, I can't just make it, the cylinder that you see there with no end caps. In other words, I can't have a soup can without a top and a bottom, because then I could go in the middle of the soup can and argue that that's the inside, but then I could go up through either the top hole or through the bottom hole and get on the outside without ever crossing a boundary or an outside edge surface. So in order for it to be a closed surface, it has to be a complete soup can. So there'd be a top of the soup can, a bottom of the soup can, and then the soup label itself. So this is what the integral of E dot dA is going to give us. I'm going to take the integral over the top plus the integral over the bottom plus the integral over the soup label, which I'll just call S sub L. Okay, just to give you an idea of what a typical dA might be on this particular surface, it might be that little pseudo rectangle right there. And this would be dA, I'll call it subscript T for top. And, you could actually work out that that's R d theta times dr. That's what it would be actually in cylindrical coordinates, but we're just going to call it dA k hat. Similarly, you could have another pseudo rectangle, and this pseudo rectangle would have a dA vector, dA bottom, that is negative dA k hat. And then also, you could, for instance, have this little surface as a little differential area element like that. And of course, that one would be dz is the vertical, and the bottom and top are r d theta again. So it would be dA would be equal to r d theta dz. and then it too would point in the r hat direction. So dA is just equal to dA r hat. So that's what we're actually doing when we're computing this integral. I'm going to come over here and say the integral over the top is going to be equal to E of r hat. Now that actually can vary over all the r's. So I'm actually literally going to have to integrate from r equals 0 to r equals r. And then I got to dot that with dA k hat. Now I got to do the same thing for the bottom. And for the bottom, I again get E of r hat dotted. And this time it's going to be dA negative k hat. So negative times the dA times k hat. And then finally for the soup label, we're going to get E of r hat dot dA r hat. Notice I did tell you if we were using those coordinate systems that I sort of introduced you to, if we were actually using those, I gave you exactly what the DAs would be, but the whole point is you don't need them specifically because you're never going to do the integral. You're just going to do the integral of dA, and that's going to be the surface area of whatever surface you're doing. So if it's a circle, it'd be pi r squared. If it's a for instance, if it's the soup label, it would be the circumference of the soup can times the height L. So it'd be 2 pi r L would be the area. So that kind of stuff. Now, the main thing is we're going to make use of the linearity of the dot product. And what we're going to get is the integral over the top of E of r dA and then r hat dot k hat, which is, y'all should know by now, the magnitude of a r hat vector is 1, and the k hat also has a hat, so its magnitude is 1. But these two are at 90-degree angles to each other, so it's the cosine of 90 degrees. So this whole quantity is just equal to 0. The other one's going to be a minus integral E of r dA r hat dot k hat, which just like before is 0. And then on this case, since we're integrating over the surface, we're going to let the argument of the electric field, the r, be the r that is the radius of the cylinder. And therefore it's a constant. So I'll get E of r out in front. Now I have the integral of dA, and then all I have left is r hat dot r hat, which is 1 times the cosine of 0. So that's just going to be 1 because the cosine of 0 is 1. So when we do all of that, we're just going to get E of r times the integral of dA for the soup label. As I said, the soup label, if you actually like took let's say you took a X-Acto knife and cut straight along here, then what you'd have is the wrapper that went like this. And that, of course, makes a shape that would make a rectangle. The length of that rectangle would be 2 pi r, and the height of that rectangle would be L. So that means we're just going to get 2 pi r times L for the left-hand side. Now I'm going to take the right-hand side. Since I use so much on that, I'm just going to say RHS right here. That's supposed to be Q enclosed over epsilon naught. So in general, that would be like a lambda times DL, but the lambda is a constant because it was uniformly distributed. Uniformly distributed, uniformly charged means lambda is a constant. So that lambda is going to come out in front, and we're just going to get the integral of DL, which is just the length of the wire that's inside the soup can. So in this case, it's just going to become lambda times L is what Q enclosed is. Whoa, Nelly. and then the epsilon 0 would be on the bottom. So now all I have to do is set the left-hand side equal to the right-hand side. So now you see that I have done my hypothesis, I've done my left-hand side, I've done my right-hand side, and now I'm going to set the left-hand side equal to the right-hand side. That's going to give me E of R times 2 pi R L is equal to lambda times L over epsilon naught. You can see from there that the L's cancel out. And ultimately, what you're left with using our hypothesis is that the electric field is actually going to be equal to lambda over 2 pi epsilon naught R, and it's going to point in the R hat direction, which, by the way, is exactly the same solution we got when we did this using Coulomb's law. Any questions on that? Now, of course, Coulomb's law use was a lot more difficult than this one. So hopefully you can see the advantage of how nice and easy this is. Anybody have any questions? All right, so now you've seen an infinite planar. We did that last time. And you've seen an infinite long cylinder. And all that's left really is to see what happens when you have a spherical shape. Now, I will advise you that we can make this a little more complicated. I don't have to always choose uniformly charged things. So for instance, I could tell you solve the same problem, but this time lambda is equal to some constant c times, let's say, y squared, where y is the distance along that. And then you could actually still solve the problem, but the right-hand side wouldn't be so easy as just lambda times L. The right-hand side is going to require you to take Q enclosed as the integral of c times y squared times dy. And then, of course, you'll have to take that Q enclosed after you compute that integral, and you'll divide it by epsilon 0, and that'll give you the right-hand side. So that's the way I can change these problems a little bit to make sure I'm giving you something new to do. So you should try to practice this by doing it yourself. Try doing this very problem with lambda equal to c times y, or lambda equal to c times z. You could put it along the z-axis. The left-hand side is still going to be the same thing. You're still going to get E of R times 2 pi RL for the left-hand side, but the right-hand side is going to be more complicated. Once you've done lambda equals C times R, I would probably in that case ask you to do it, but I'd also ask you what if the total charge of a length of 4 meters is 6 microcoulombs, then what is the constant C and what units does it have? So that would be another follow-up question I'd usually ask. So that's something you can try to do to make some sense of this and to just get some more practice. But the bare minimum is you should be able to take that infinite plane I did yesterday or last time and be able to do that on your own without looking at the video or without looking at your notes. Then you should be able to do this one without looking at the video or looking at your notes. And then you should be able to do these other ones I'm getting ready to show you. So right now I'm going to show you a little more complicated problem. I'm going to take a uniformly charged spherical, actual spherical chunk of non-conductor. Okay. So here we go. Let's say a sphere, a solid sphere is made of a dielectric material. Dielectric, remember, is just a fancy word for insulator. Okay. A solid sphere is made of a dielectric material, and has a total charge Q distributed uniformly through, whoa, Nelly, THROUGHOUT, throughout its body. Its radius is R. Use Gauss's law to compute the electric field for R less than big R and for R greater than big R. Okay. So the fact that it's uniformly distributed throughout means that the whole solid, every little millimeter cube of it, will have a certain amount of charge, and that charge divided by 1 cubic millimeter will be the charge density rho. And if you grab another piece that maybe instead of being a millimeter by a millimeter by a millimeter, that one might be 2 centimeters by 3 centimeters by 1 centimeter. If you found out how much charge was on that and divided it by that volume and converted it to volume per square or per cubic millimeter, it would have the exact same value. So that's what that lambda is. So now I'm going to work it by first embedding it in a coordinate system so I can make use of the various vectors we have at our disposal. So I am going to draw a coordinate system like this, and I wanted it to be perfect, so I forgot to push the button. So I'm going to do this as well, and I'm going to do this as well. Okay, so this axis right here is going to be my x-axis. This axis right here is going to be my y-axis. And this axis right here is going to be my z-axis. Now I'm going to draw a sphere. And I don't want it too terribly big. But I don't want it too terribly small either. That actually worked out pretty good. So that's actually going to be the spherical charge distribution. You know, actually, I think I do want it bigger than that. Let's see if I can make it bigger. Heck yeah, I can. Okay. So that's going to be the charged sphere. And it has a radius, of course. A radius equal to big R. Like that. Dang it. It keeps making it into something weird. Okay, and it has a total charge Q. And that Q is all the way through it, okay? Now, just to convince everybody that it is actually a sphere, I'll do that so it looks a little bit more three-dimensional, if you will. Now, I'm going to go ahead and write solution right here. And I'm going to say the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And I'm going to say my hypothesis is that E, the electric field, is going to be some E of R, and it's going to point radially outward with the actual spherical coordinate R now. So this is the spherical coordinate R hat, not the or the spherical coordinate vector. r hat, not the one from cylindrical coordinates. So it actually does have an or excuse me, an I hat, a J hat, and a K hat component in general. So there's my hypothesis, and I'm going to say that for everywhere, for all R. Okay. Now I'm going to have to attack a specific problem, which is R less than big R, and I'm going to write left-hand side. Okay. Now, in order to do this, I need a Gaussian surface. So I'm going to choose a Gaussian surface that is basically, we need to find a surface that should be at least have an electric field that's constant on the surface, or at least on some part of it. Now, since I've argued that the electric field is E as a function of the spherical R and pointing in the R hat direction, then that tells me if I choose a concentric sphere, in other words, a sphere centered on the origin, just like the charged sphere is, then the electric field on that surface of that sphere should be a constant everywhere. So that's exactly what I want as far as my Gaussian surface goes. So now what I'm going to do is try to draw a really good Gaussian surface like this. And that was supposed to be a perfect circle. Close enough. And again, it is a circle, so I'll try to so I will try to make it look a little bit more round, like that. Okay, so that's our Gaussian surface. And that's for R less than R. Okay, and obviously that means R is just the radius of that little sphere. So the left-hand side is the closed integral of E dot dA. Well, that's going to equal the integral of E of spherical R times spherical R hat, dotted with, now this time, the little differential area element will be this little guy right here. And that's just going to be dA R hat again. Again, that's the spherical coordinates dA. Now, in principle, you could work out what that is using spherical coordinates and double or triple integrals, in this case, a double integral. And that's fine, but you really don't need to know it because remember, we're not supposed to actually conduct the integral on the left-hand side, right? But for the record, it would be R sine phi, no, R squared sine phi d theta d phi. That's it. But again, you don't need it. So I'm just going to write it as dA R hat. And now I'm going to use my linearity property and recognize that on the surface of the sphere, the electric field is in fact a constant at radius R. So I'll pull that out in front and say E of R times the integral of dA times R hat dot R hat. And we've already figured out that R hat dot R hat is 1. So what I get is E of R times the integral of dA. That means the surface area of the surface we're integrating. The surface we're integrating over is a spherical surface, and the surface area of a sphere is 4 pi r squared. So now we have the left-hand side of Gauss's law for R less than R. The right-hand side for Gauss's law is Q enclosed over epsilon naught, and that's a little bit complicated. Okay, in principle, what we could do is just use the integral of rho dv. So we could say the integral rho dv over epsilon naught, and that works fine. And I'm going to show you real quick what it would be. So first off, I would say rho has got to equal, remember rho is the charge per unit volume. Can anybody tell me what the total charge on this and I'm saying the total charge of the whole sphere. We're not yet working on the sphere that I've got inside, but on the total blue sphere, can anybody tell me what the total charge is or what symbol we've assigned it? Let me check my chat, see if anybody's trying to type it in. I'm not feeling confident. Nope, I've got a lot of names, but no guesses. Nobody has an idea what the total charge on that blue sphere might be based on the blue words above? Yes. Tanika did give me the right units. You know it's going to be coulombs per cubic meter. Now, did we assign a symbol for the coulombs though? So the main thing I'm shooting at here is I told everybody that the total charge was distributed uniformly throughout. So that means rho is going to be a constant. And we know one specific value of that constant. Specifically, it's the total charge of the blue sphere divided by the total volume of the blue sphere. So does anyone know what that would be? Can anybody come up with a formula for that? I'm going to say sidebar. Since it's a uniformly charged sphere, the total charge is Q, and the volume of the sphere is 4/3 pi r cubed. So I'm going to write 4 pi r cubed, and the 3 will go up top because it's supposed to be 4/3. So that is our actual charge density. So we could actually do that and then choose a specific charge, our differential volume element so that we can integrate it. And this time we'd integrate not from R to big R, but from R to little r. So if I wish to do that, I can do that right now. I can say equals 1 over epsilon naught, and I'll say the integral of 3q over 4 pi r cubed. That's my rho. And my volume, I'm going to say, is like if I imagined a spherical shell. That spherical shell would have a radius r, and its area would be 4 pi r squared. But if I multiplied that area 4 pi r squared by dr, then that's approximately equal to the volume of the spherical shell. Now, I've computed this over and over again and shown you exactly what that spherical shell would be. And it turns out this is perfectly fine to do it, but this is the way we would have done it in calculus. So I'm going to say the differential volume element is 4 pi r squared dr. So that's the spherical shell. Now we can pull the 3q over 4 pi epsilon naught r cubed out in front because that's all constants. So I'm going to put 3q over 4 pi epsilon naught r cubed. That's all in front. Plus the 4 pi from the 4 pi r squared in dv goes there. And now I have the integral of r squared dr from r equals 0 to lowercase r. Now, the integral of r squared, by the way, this 4 pi cancels out with this 4 pi, but the integral of r squared is 1/3 r cubed. So I'm going to say this quantity right here is 1/3 r cubed evaluated at r equals 0 and then r equals r, which clearly gives you just 1/3 r cubed. So now what we're going to have is the 1/3 is going to cancel out with the 3 next to the q, and we're just going to get q r cubed over epsilon naught r cubed. Okay. So that actually works, and we're ready to go with that. But here's a way without calculus. Since it's uniformly distributed, we know rho is a constant. So that means the rho of the blue sphere is the same as the rho inside the green sphere. So I'm just going to write that and say rho equals a constant, which is equal to 3q over 4 pi r cubed, but that's also equal to 3q enclosed over 4 pi r cubed. And if you solve this, you get q enclosed is equal to q times r cubed over r cubed, which you can see is exactly the same answer. Okay. So y'all see the only difference between these two is the top one has the epsilon 0 already in it, whereas the bottom one doesn't. So there's two ways you can do this, and doing the integral way actually shows you what would have to happen in the event of doing a spherical charge distribution. Assuming the charge density was a function of r, you'd need the differential area element to only differ in r by a differential amount. So the spherical shell would be the choice that you want to make. But now that I have this, all I have to do is go ahead and set left-hand side equal to right-hand side. So left-hand side equals right-hand side gives me the following. I'm going to get E of r times 4 pi r squared is equal to q r cubed over epsilon naught big R cubed. Now, in this case, you can see that the whole r squared cancels out with the whole 3, but leaves the r there. In fact, this tells us that the electric field is ultimately equal to, using my hypothesis, is equal to q over 4 pi epsilon naught r cubed times r hat. That's what's showing us that this is actually a linear electric field, meaning if I double the distance away while I'm still inside of the charge that we have, then I double the electric field strength. Whereas normally, if I double the electric field strength outside of if I double the distance away outside of a charge distribution, then the electric field actually goes down, and not by a factor of 2, but by a factor of 4. This is one where, because the charge inside of the Gaussian surface is increasing as r increases, the electric field would generally decrease as 1 over r squared, but the charge is actually increasing as r cubed. So it basically wins in that the charge outweighs the degradation or the diminution of the electric field, so that you get a r on top instead of a 1 over r squared. All right, so I've got that one. Now all I have to do is the same thing for r greater than big R. So how do we do that? Well, I say r greater than big R, and then I say left-hand side. Okay, now this Gaussian surface is going to look just like the last one, except now it's got to be larger. So what I'm going to do is try to draw another Gaussian surface and try to use the tools that this program gives me, and that's it. Okay, so that's my new Gaussian surface. And that's for this guy right here. So now I have that new Gaussian surface, but everything's going to be the same. So the closed integral of E dot dA, let me show you what this would look like in when you're actually doing it. I would really like you to basically just show that it's E of R times dA times R hat dot R hat equals E of R times 4 pi R squared. That's it. Okay, all that other stuff I've been doing is me trying to explain what's going on, but you don't have to do all that. For instance, in the when we did the infinite plane last time, I did the top of the soup can, I did the bottom of the soup can, and I did the soup label. If you showed me those three integrals and you showed me the R hat dot K hats dropping out, that would be plenty. Okay. In fact, if you got the answer right and just went from closed integral E dot dA to just EA plus EA plus 0, I would give you full credit on that. Okay. Now, the right-hand side, which is normally the harder side, in this case is super easy. It's Q enclosed over epsilon naught. But since I made the sphere big enough to enclose the whole charge, the Q enclosed is just Q. So the right-hand side becomes Q enclosed over epsilon naught. And then I set left-hand side equal to right-hand side like this. And when I do that, I get E of R times 4 pi R squared is equal to Q over epsilon naught. And I bet you're going to find this looks a lot like Coulomb's law. It's going to be Q over 4 pi epsilon naught R squared R hat. And of course, that is exactly Coulomb's law. I'm really bothered by how bad that part over there looks, so I'm going to rewrite it. So that's the actual electric field for R greater than big R. So this one I should say for R less than big R, and this one for R greater than big R. But if you look at that closely, what you'll see is that if you replace little r with big R in both formulas, you get exactly the same answer. So now I can go back and put a equal to under both of those so that the electric field is actually going to be continuous, even though its derivatives will not be continuous. So one of the other things that we often ask our students to do in this chapter is we ask them to plot the magnitude of the electric field as a function of distance. So in this case, as a function of r. So what I'm going to do is draw a coordinate system like so. Actually, I should have done that neatly, so I'll do it again. So there's my electric field axis. And there's my radius axis. So R and E. And what I'm going to do is say that Q over 4 pi epsilon naught R squared is a particular value. And in fact, I'm going to say that when R is equal to big R, that's exactly the value we get. So I'll put a dot right there. Now, what I have to remember is that this electric field for R less than R is just linear. And not only that, it's not only linear, it's linear with no y-intercept. In other words, the y-intercept is 0. So it's just a diagonal line from the origin to that dot. So that's the electric field for R less than R. And then for R greater than R, it falls off as 1 over R squared, just like that. And that's what the electric field looks like. Notice it is actually continuous. Even though the slopes are not, you can see right there at the point R, the slopes are not continuous, but the electric field at R coming from the left is the same value as the electric field at R coming from the right. Therefore, it's continuous. Anybody have any questions on that? All right, so let's try another. This time, what I'm going to do is sort of show you the same thing, but this time we're going to do a solid conducting sphere. Okay. So let's say given a conducting solid sphere of radius, oops, I should have wrote that, of radius R and total charge Q, compute the electric field everywhere. Okay, so there's our problem. I'm going to start off with a coordinate system again. Okay. Now, this is my x-axis, this is my y-axis, this is my z-axis. As I've told you 1,000 times, it's supposed to be consistent with the right-hand rule. I hat cross j hat gives me k hat. This meets that criteria. I'm going to draw the sphere in blue, and I'm going to assume it's about this big. Oh, no. I'm going to assume it's about this big. And let the thing fix my drawing, and it did a good job. Okay. This sphere has a radius big R and has a total charge Q like that. And it is a sphere. So I'll try to make it look a little bit more spherical by adding this detail. And now I'm going to write out solution. Again, we're going to make use of Gauss's law. The closed integral at E dot dA is equal to Q enclosed over epsilon naught. I'm also going to make the hypothesis that E is equal to E of R hat everywhere. Now, here's the problem. Gauss's law can be used to show us something. So one of the things we know specifically is that in electrostatics, so I'll write it here, in electrostatic situations, and that means no moving charges. Electrostatic situations, the electric field in a conductor is 0. Now, the reason that's the case is if there was an electric field inside of the conductor, conductors are objects are materials which has free electrons that are able to move around the whole chunk of material. So if there was electric field in there, the charges would move, which violates the idea of it being electrostatic. So because of that, you can use Gauss's law and imagine a Gaussian surface just inside of this conducting sphere. So if you imagine a Gaussian sphere just inside the outer edge of this sphere, then everywhere inside of there, the electric field had to be zero. So the closed integral of E dot dA is equal to zero. And since Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught, and the closed integral E dot dA is zero, that means the Q enclosed is zero. So we're able to reach the conclusion that when you're dealing with a conductor, all of the charge in electrostatic situations will reside on the outside surface. It'll actually orient itself so that it distributes itself uniformly on the outside surface. So it basically has a uniform surface charge density, sigma. Okay, that's the difference between a conductor and a non-conductor, like we just looked at. Okay, so now that I use that, I can examine a few things, but I had to get that statement out to you. So what I'm going to do now is I'm going to draw my Gaussian surface. Maybe this time I'll make it a nice shade of green again. No, I don't like green. Let's do a nice shade of pinkish. Okay, so I'm going to do a Gaussian surface for r less than big R. Like that. That's the Gaussian surface. And this is for r less than big R. And then I'll go ahead and make the other Gaussian surface as well for r greater than big R. And it's going to be like that. And now that I have those, I can make this a little bit more realistic by putting that little bit of curve in it. And I'm going to do the same thing here. Like that. Okay. So this radius of this little sphere is R. And of course, later on, that radius of that bigger sphere will also be R. So I'll just put it there like that and say this one's also Gaussian. Okay. So now we'll get back to where we were starting. I'm going to say R less than big R. Left-hand side. Closed integral E dot dA is equal to Q enclosed. Oops, stupid head. I started to write the whole equation again. Okay. In this case, it's actually equal to the integral of E of R hat, dotted with dA R hat, which equals E of R times the integral dA times R hat dot R hat, which is just, I won't try to fit it there. I'm going to come around here and say this is just equal to E of R times 4 pi R squared. Now I'm going to say the right-hand side is equal to Q enclosed over epsilon naught. But as we just decided, all the charge is going to be on the outside surface. And it will be literally uniformly distributed over the top. It's got to be uniformly distributed because all of the charges that are on the outside surface have to get themselves equidistance away from all the other charges so that they're minimizing the energy stored and being near each other. You got a bunch of positive charges. They don't like being near each other, so they're going to space themselves apart as far as possible. And since it's a uniform spherical shape, that's going to make them basically orient themselves in a uniform pattern on the outside. So with that in mind, we can now say that Q enclosed over epsilon naught is just 0. So now I say left-hand side equals right-hand side. And this gives me E of R times 4 pi R squared is equal to 0, which means E of R equals 0 for R less than big R. Now I can try R greater than big R. Okay. Did everybody follow what happened with the R less than big R? Okay, no questions? All right, I will continue. Left-hand side, closed integral E dot dA is equal to the integral of E of R hat dotted with dA R hat, which equals E of R times the integral dA of R hat dot R hat, which is equal to E of R times 4 pi R squared. Y'all seeing a pattern? Hopefully by now it's obvious what the left-hand side is always going to be equal to. Now I'm going to do the right-hand side. Q enclosed over epsilon naught. Since I'm doing this outer Gaussian surface and that radius R is bigger than big R, you know the entire charge has been enclosed. So this side's just going to be Q over epsilon naught. So now I can say left-hand side equals right-hand side. And this gives me E of R times 4 pi R squared, is equal to Q over epsilon naught. So E is equal to Q over 4 pi epsilon naught R squared R hat for R greater than big R. I'm going to write that somewhere else so it's not crunched up in there. Okay, and now I'm going to pull out my red marker and box off that answer and box off that answer. So now what I have is a electric field that we can again graph. Okay, this is my R axis. This is my E axis. And this is Q over 4 pi epsilon naught R squared. This is going to be R. And of course, once you do R equal to big R, you're going to actually get a dot right there. But the electric field is in fact going to be 0 up until that point, and then it discontinuously jumps up here. Darn it. It discontinuously jumps up here and falls off proportional to 1 over R squared. Now, notice the discontinuity. I'm going to do it this way. Let's say I'm going to take, let's take this, oops. I'm going to take this red marker. And I'm going to say, this distance right here is the discontinuity. Equals E on the plus side minus E on the minus side, which equals, in this case, Q over 4 pi epsilon naught R squared minus 0. which you might notice is equal to Q over 4 pi r squared over epsilon naught, which is also equal to, let's see, that's Q over 4 pi r squared. We got that. We got the minus side would be the 0. That looks good. And of course, that Q over 4 pi r squared is actually just the surface charge. So this would be sigma over epsilon naught. So we get that the discontinuity is actually equal to sigma over epsilon naught. Now that's also consistent with what we found on the discontinuity for the electric field of a infinite plane. Remember, above it, it was sigma over 2 epsilon naught, and then below it was sigma over, or negative sigma over 2 epsilon naught. So you do sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught. That gave you sigma over epsilon naught as the discontinuity. So that turns out to be a fundamental rule about the components of the electric field perpendicular to a surface. So whenever a electric field goes from one surface or from one material to the next, the component that's perpendicular to it is going to be continuous unless there's a charge, a surface charge. If there is a surface charge, then that discontinuity will be the surface charge divided by epsilon 0. Anybody have any questions on that? Okay, so that is a really good example of Gauss's law. Again, I could soup that up, or I could soup the other one up and use a, for instance, the other one I used a rho. I could use a rho that's equal to some constant C or K times, R squared or R to the fourth or something like that. And then it's a slightly different problem. The left-hand side is still going to be the same way, but the right-hand side, calculating Q enclosed over epsilon naught, would actually involve you having no choice but to take an integral. So anybody have any questions on that one? All right, well, we don't really have enough time to jump into the next chapter, and I've done more or less all we need to do. I will encourage you to read the Gauss's Law chapter. It's one of the shortest chapters, but it has a lot of pertinent conceptual information that you need to know. For instance, the fact that a conductor has a 0 electric field inside. And because of that, that means that whenever you have a conductor in an electrostatic situation and you put a charge on it, that charge will automatically go out to the outside edges, just to reduce the, another way of thinking of it is just to reduce the energy stored up, because obviously when you get charges near each other, that makes some potential energy, and they're always going to try to minimize that potential energy on their own. So the Q is going to go out as far as possible, which means the outside surfaces, and then it's going to uniformly distribute itself over the outside surface so that all of them sort of have their maximum separation between each adjacent Q's. Okay. Now we can do stuff like that and use stuff like that like this. So imagine for a second, I'm just going to do one little quick example. Let's take a blob of material. So that's supposed to be a blob of material that is a conductor, okay? And I mean, it's going to be a three-dimensional surface like this. Okay, and now let's imagine that inside of it is actually a cavity like that. So that just means an empty hole. And let's say it has a charge of plus Q on it. So if I put a charge of plus Q, what's going to happen, according to what I just taught you, is the outside edges of this are going to get covered with a charge Q all distributed over the outside. and it's going to distribute itself somewhat uniformly as best it can to minimize the amount of energy resulting from positive charges being next to each other. But now, if I were to teleport, for instance, a charge of little q inside that cavity, then what's going to happen is if we took Gauss's law and we imagined a Gaussian surface just inside of the cavity, then we'd actually get an electric field all inside of that cavity. And that electric field would be q, little q over 4 pi epsilon naught r squared, where r is the distance from that little charge, little q, right? Now, if I were to take a Gaussian surface just outside of the cavity like this, we know that electric field has to be 0, and because it's inside the conductor. So what's going to happen is the total charge inside of that Gaussian surface must in fact be positive, or excuse me, must be 0. And the only way I could do that is by adding a bunch of little let's say little negative charges all on the inside surface, such that they add up to a negative lowercase q. Okay. Now that's also going to cause, because these are negative, it's going to force an additional charge to go on the outside, so that now you're going to have this positive charge here and here and here and here and here. It's going to distribute itself uniformly, but the main thing is I'm trying to draw another color of positive, so you'll realize that because I put that in there, now I've got even more charge, and now the charge after teleporting positive q into the cavity. Whoa. The total charge is q plus big Q. So, and it's all on the outside. And of course, the charge inside is negative little q. On inside wall. All right, so that's the last part. You guys are free to go. Make sure you chat me your first and last name if you hadn't already. I'll wait for the last person to leave in case anybody has any questions, but you guys have a good, safe weekend. Get your tests done. I'm going to send an email to the testing center to include the hours up through Monday. I don't think I did that already, so I'm going to go ahead and do it. But you guys are free to go. Thanks for coming, everybody.
Hey, Professor, quick question. I had heard you mention earlier to that, just to let you know when we were going to take the tests. Do you just want us to let you know, like via text, so that way you can pop on during that time frame, or what would be easiest way to let you know?
Yes, send me a text or an email, just knowing what time and what day you're planning on taking it, so I can make sure I get everything set up by then. I'm going to actually, there will be a different test. It'll be called, it'll have something inside of it recommending or showing that it's for people taking it at home. But you'll see it also being different because instead of having a lockdown browser, it'll have the lockdown browser plus Respondus Monitor on it. That's the one you guys will have to take.
Okay,
So
I'm
just let me
aiming
know
to
the
take
day
it.
and time.
Okay, yeah, I'm aiming to take it either Sunday morning or Sunday evening. It just depends on how much studying I get done tomorrow and Saturday.
Okay.
So I'll
Well,
just
what
shoot
you
you a
were
text.
saying then would be even better. Yeah. So if you tell me, if you send me an email saying sometime on Sunday, I'm not sure if it's morning or evening, do that. And then, like you said, just text me just before you get ready to start. And that way I can pop on if I need to.
Perfect. Thank you.
Thanks, Carter. Have a good one. Good luck.
You too. Bye.
Bye-bye. Anybody else?
I guess I'll go next. So I think this is good news. I was talking to my manager today. I was like, "Is there any way I could borrow this mirror?" And he's like, "What in the world do you need a mirror for?" And I was talking to them, and they're like, well, oh my gosh, do you want me to like proctor? Like your professor can email me or I'll sign whatever I need to. I was
Oh,
like,
that's cool.
I know he was offering some people to proctor, but I don't know if like our manager could. So I was like, I'd ask. Because I figured that might be better than Respondus, but I wanted to like get your opinion.
Whichever you prefer. And the big thing is when I have someone that is willing to proctor and they're in someone's chain of command, I defer to the student in that case, because I don't want to put someone in a bind where their higher up might take advantage of them or something like that. So as long as you're okay with it, I'll be okay with it. Or you can just do it the way it was by borrowing the mirror. Just let me know whichever one you do, and I'll
Okay.
send them a long wordy request of what has to be done.
Okay, so you just want their email or what?
Yeah, their
Or
email would be fine. And I can send them an email. I need their full name, of course, in their email, or they can contact me with their full name, and they can text me directly. That's the way I
okay,
handled it today, was just by text. They can text me that way.
okay, yeah, I think either manager would love to do it, but I know if it's Scott, he's like, yeah, I'd love to take, because he's big on like no phones at work. So he's like, I'd love to take your phone for an hour while you go to yeah, or like leave it in his office. He'd be all
Oh,
over
you love
that.
that,
So
huh?
okay,
That's
I'll
good.
give it. I'll see who's on tomorrow, and I will send somebody's information.
No
And take
problem.
it at work because they were like, well, you could take it in the like the lounge. I was like, really? He's like, yeah, just clock
That's
out.
good.
I was like, okay, bet.
Good
So
deal.
okay, I'll do that.
All right. Well, that's good. Sounds good, Hannah. Just let me know what time you plan on doing it and all that good stuff, and I'll and when I get a text from them, I'll respond to them with all the details.
Okay, awesome. Thank you so much, Professor Younger.
You're welcome. Feel free to print out the copy of the equation sheet that I posted on your check Canvas page and take that in
Yes.
with you, because I'll let the instructors know, the proctors know, and I at least give them a copy of it so that they can verify that it's the same as the one that you have.
Okay, gotcha. And then I can have I have a TI 84. I don't think I've ever had like my calculator checked, but
Yeah, I don't
that's
mind. Any of
fine.
the calculators are fine with me, as long as they're not on a tablet or a phone.
Okay, nope, not on a tablet or phone. Got it. Okay. Yep, I will send you their information.
All right, thanks, Anna. Have a good one.
Thank you. Have a good one.
Hey, Micah, you have any questions for me? Might not even be there, huh? I do not believe Micah is still here. So, bye, everybody. Thanks for coming.